Okay, morning everyone. We'll get started in 30 seconds or so just start settling down. Thanks. Okay, so here we are, lecture 10, coming to the end of part 1, and as usual a few things to point out before we start. Please take note of these updated staying safe on campus notes that we've been asked to circulate to you all. Do what you can to adhere to them. They're also on the PDF uploaded onto Blackboard. Okay, so updates to Blackboard itself. We have added a bunch of past papers from previous years. I'll run through them for you to have just to point out a few important things. We've also, I didn't make a note here, but we uploaded the lab handbook, and the first fluids lab is tomorrow. So again, make sure that you check your individual timetables to see if that includes you. It'll be 16 people tomorrow, and then every week there's a number of labs for the next 5 weeks. So check when yours is. Just to point that out to you. So if you go to this, you see all the possible lab slots for mech and aero. We can't give you the list of names. We can't put a list to say which one you're on Blackboard, but if you check your timetable for mech and aero and you don't find yourself in any of the green slots for your cohort, let me know and we'll follow that up. There's also pre-read material here. This gives you an outline of what you do in the lab, the activities that you'll cover. We won't be providing paper handouts at the lab in line with our kind of aims to reduce paper waste. So we're putting them online now for you. Make notes directly onto these, I would say. There's a bunch of diagrams provided for you to sketch, or you can print your own, of course, to sketch the flow or to make notes of the flow during the lab. These are the kind of things you're going to be testing. And at the end, there's a bunch of questions that you'll discuss as a group at the end of the lab. And there's also some supplementary information. A lot of this is summarizing the last section of Chapter 1 of the Frank White textbook, where it talks about FlowViz. And a reminder that this lab isn't assessed, so you don't have to submit anything. But you'll be given 5% if you turn up and you've engaged in the proceedings. Okay, so that's the lab. Any questions? Let us know. And then here's the past exam papers. So, past exam papers, they're organized into 2 folders. 3. This course has been running for a long time, and it's been kind of updated every five years or so. The first time that Professor Ben Rogers and I did this course was last year or the year before. We did half of it the year before, so it's just starting to be updated. So although probably around 90% of the content is the same, there may be some slight changes when you start to look at the older exam format. So if any questions arise, use Piazza to address them. So in many cases, there are video solutions. Some of them provided by kind of our current team, so Marta, and some of them provided by maybe previous lecturers, but they're all still relevant, very useful as a kind of learning resource. Again, remember that in the older versions of the course, things might be explained in a slightly different way. That's not usually a bad thing. Understanding something explained different ways is a good way to consolidate your understanding. But just, be aware that there might be some methods used that we haven't discussed yet. At the end of the day, your aim is to get the right answer, so it doesn't really matter what method you use. As long as you explain that in the exam, the method that you've used, then you'll get the marks. Okay, so today's lecture is on conservation of momentum. It's the last one in part 1. Next week, there isn't any lectures, so I won't be lecturing you on Monday or Thursday next week. But here's a question for you. There's a couple of people who have pointed out they've got a number of questions that they would like a bit more support on. And what we thought we would run, entirely optional basis, is kind of like a drop-in surgery run by GTAs if you want to turn up and ask them questions. Okay, so the proposal is that next Monday, 10 till 11, the usual slot in Reynolds Lecture Theatre, that there isn't going to be a lecture, but there'll be a handful of GTAs, four GTAs or so, on hand to go round and respond to any questions that you have. Would you be interested? Hands? Yeah, there's enough people. Okay, we'll do it. Okay, and so, like I say, it won't be like a class-led thing, but it'll be a chance to kind of, get a bit more support. Okay, good. I'll send an announcement around about that. Right, so moving into today's lecture, conservation of momentum. It's one of the three kind of pillars of fluid mechanics and the integral analysis and differential analysis that we use. We're going to look at that. We're going to talk a little bit about that in the context of what you've done in physics before, what we've been discussing already, and what you're going to be looking at next semester in your mechanics or dynamics module. So trying to make some links and connections between what you're going to be hearing again next semester. We'll talk more about some practical assumptions and considerations. And then there's a bunch of examples. If we don't get through all of the examples, I'll upload the full solutions for you to have a look through in your own time. But we'll see how far we get. Okay. Start off with a bit of discussion. So Newton's laws are, underpin a lot of our kind of continuum analysis, and it's very important that you're kind of familiar with what they mean, where they come from, what is their fundamental objective and their practical use in engineering. So here's one. Here's a picture commonly used and commonly seen. Which of the Newton's laws is this describing, and why? There's more than one answer. So who wants to start us off? Yeah? Yeah, so which of Newton's laws is this describing? Yeah. F equals ma. Yeah, excellent. And this, for bonus points, what's your thinking behind that? Yeah. Okay, so this is the kind of thought experiment, Newton's cannon, where a force is applied to a cannonball, and according to the magnitude of that force, it achieves a different acceleration, a proportional acceleration. Eventually, if the acceleration that it is given is equal to the acceleration required to maintain a circular path of a radius equal to orbit, then it stays in orbit. If the acceleration that it has is less, then it doesn't reach orbit and it falls to the ground before it completes a circle. This is something that aerospace, you're going to look at more in your space systems next year. But it underpins a fundamental, probably the most important law, Newton's second law, F equals ma. The force is directly proportional to the resulting acceleration, or vice versa. How about this one? So, just, they shouldn't come up at once, but okay, the central figure, what's going on there? Yeah? Yeah, how come? Yeah, that's right. So how is that being described by the center picture? Yep. Onto the plane. Yep. Yeah, excellent answer. Yeah, so here you've got an example of Newton's first law, which is largely based on Galileo's work, recognizing the concept of an inertia. An inertia is essentially a momentum, a property of a body that, in the absence of additional forces, it will maintain. And here you have an exchange of energy, potential to kinetic, resulting in the ball having a velocity on the horizontal plane. And in the absence of friction, it will continue to have the same velocity for infinity. And that's the quantity that that ball has is known as inertia. And the inertia is Newton's first law. And then, by process of an elimination, you can probably guess that the last one is Newton's third law. Every force has an equal and opposite reaction. A classic example of that is the rocket. And it's a bit of a chicken and egg situation. When you think about, what force is leading to what force in an equilibrium situation, it's sometimes easy to get a bit confused. But the situation is most clearly understood in equilibrium. So when you're thinking about Newton's third law, to start with, think about it in an equilibrium way. When you stand or sit in a chair, your weight is cancelled by the reaction force supporting you. Slightly more complicated if you're in a lift and you jump when the lift is going up or down, because the reaction force won't be equal necessarily to your weight. It will be a sum of your weight and the acceleration the lift is going in. But like I said, to start with, think about the situation in equilibrium. Okay, so here you've got basically the summary of what we just said. I put it here for background and for revision. Try to, if you're not already kind of familiar and able to identify those forces, kind of those laws directly already, revise it and be prepared to be able to do that in the future. It's really useful. Like I say, though, the one that we're focusing on today is the second one. And this is what we introduced on Monday. This is our mathematical framework when we introduce control volumes and we apply the conservation laws to the control volumes. We show here conservation of mass and conservation of momentum. And we noted a few extra things. I repeated the slides here for convenience, but I won't go into too much detail. Basically, the overall sum of the change is equal to the change within the control volume and the change across the control volume borders. And that technique, that philosophy, can be applied to any quantity that you want to track. When we think about momentum, specifically, it's instructive to note that that d by dt term is essentially F equals ma. It's the rate of change of momentum. And the rate of change of momentum is going to lead to the sum of the forces. So on the left-hand side of this equation, you have the sum of the forces applied to a system. If it's steady, then that term drops out. And like we said on Monday, this equation can then be simplified to be the sum of the forces as equal to the change in momentum, or momentum flux. More specifically, because we have m dot, which is our mass flow rate. So hands up if you've heard of impulse before. Excellent. That's pretty much everybody. Impulse is essentially exactly the same thing in a more general way. Impulse is a force times a change in time. A force times a change in time is equal to a change in momentum. And that's exactly what we have in this equation. The difference is that we don't have a solid, or we have a mass of fluid which is changing, which is flowing with a rate of m dot, the mass flow rate. But otherwise, it's essentially the same thing. And so I've included a couple of slides here, not for you to have to worry about too much right now, but to prepare you for what's coming up in semester 2, which is, I think, probably another quite challenging module called mechanics, where you start to look at the dynamics of solids, the relation between kinetics and kinematics, and various different control systems. And underpinning that, of course, is going to be linear momentum as well. Linear momentum is directly related to Newton's second law, as explained here. The acceleration is the rate of change of the velocity, which is then equal to the rate of change of momentum. And you can understand that in simple terms, or in point mechanics terms, by the change in the direction that an object undergoes following the application of a force. And that's what's explained in the vector diagram, which always makes things look more complicated, but it's exactly the same principle described in 3D. And here's your kind of what we had on the previous slide, where our dt is gathered between the two terms to emphasize that it's the same thing. Of course, if there is no force that's applied, then there is no change in momentum. If the sum of the external forces is 0, then there won't be a net change in momentum. And in this slide, we are just comparing side by side the definitions that we are referring to. The definition of an impulse, which is a change in momentum. You can think about this intuitively as the time taken to impart the change. If you have an object that is traveling at a velocity, has a certain momentum, m1, and you're bringing that to a stop at point m2, then the impulse is going to be a function of how fast you intend to do that change. If you're catching a ball and you don't move your hands with the ball as you slow the ball, then the force required is higher because the time interval is lower. And then conversely, as we're taught to catch the ball and move our hands to increase the period of time that the ball is decelerating, and that reduces the force required to bring the ball to a stop. The impulse is the sum of the force and the time interval. And it's exactly the same in fluids. Here is a classic example, kind of analogous to the catching of the ball. You have flow coming out, hitting a plate. It imparts a force on the plate. And the force that is imparted on the plate is proportional to how much mass is hitting the plate per unit time, the mass flow rate. If the mass flow rate is low, the force is going to be low. If it's higher, it's going to be higher. We have some more examples of that later on. Any thoughts, any reflections on what we've talked about so far? It's interesting to note that this is something that you're very familiar with, and yet it has been derived from something that is a lot more complicated, right? So that's key, because why do we show you the complicated equations at the beginning? Because they are the fundamental understanding and description of the mechanics. Everything that you've been taught previously, you've kind of been taught as a shortcut. You've been taught, okay, the way to solve this problem is to use an assumption like this, but you might not necessarily have been taught how to reach that shortcut. Now, we're introducing to you the full equations and the series of assumptions that you can choose to take so that you can make informed decisions about which equations to use. That's a recurring theme. A lot of what you're taught prior to the start of your degree will have been on a need-to-know basis, and now we're telling you how to understand the full picture, and you decide what you need to know. That makes sense. Okay, so kind of summarizing what we've been doing then, we've got this kind of conservation equations, which are the fundamental pillars of fluid mechanics. The conservation of mass, which is our mass flow rate times the density, the area, which is the mass flow is equal to the density times the area and the velocity, our momentum, flux. And what we haven't looked at yet, that you're going to look at in part 2, the conservation of energy leads to the Bernoulli equations. The Bernoulli equation is an expression to describe the interchange of kinetic and potential energy, as well as the internal energy, which is essentially the pressure. Remember we said at the beginning, right at the very beginning, that pressure is a thermodynamic quantity. It's represented by the kind of the velocity of particles and how frequently they impact on a surface, so that the pressure is already an energy. It's an internal energy of a fluid. If you increase the pressure, then it's going to have a higher energy. But don't worry about that for now. In a couple of weeks, you'll talk more about that with Professor Rogers. But important to note that those 3 laws, they underpin the analysis you're doing this year and a substantial amount of what you do next year, and they have been derived from that much more complex analysis. That's the key thing here. Okay, so let's move on to some more practical considerations, the kind of common scenarios, assumptions, approximations that you're likely to need to use now. So, first one is one we've talked about several times, including last week, I think also on Monday, is the concept of 1D simplification. It's not immediately straightforward. When you think of 1D, you usually think it has to all be in a line, a linear change, but that's negating the possibility to use an intrinsic coordinate system. And there's some examples here. So if I tell you we're only going to study 1D problems, you might immediately think of this. A tube with a flow going through it where the walls of the tube are parallel and nothing else is changing. If I said, okay, we're going to apply 1D analysis to this problem, hopefully you'd probably already be convinced that we can do this by just noting that the cross-section area is changing. If I then said, okay, we can apply it also to this problem, you might start to doubt me, because clearly this is changing in 2 coordinate directions. But the point is the intrinsic coordinate. If we can find a way to represent this in 1D, then we should use 1D equations. And here, the intrinsic coordinate is basically a local coordinate system which is changing as you move along a path. You're going to do this in a lot more detail next year. And it's a very useful way to simplify problems like this. All of these can be used, you can apply the 1D equations that we summarized in the previous slides. Again, you have to make sure that everything is in that same direction, along that same coordinate system. Here, our coordinate system is the red curved line on the right. The force is aligned to that, so we can apply our force. Our external force applied to this control volume is going to result in a change in the mass flow rate times the velocity between points 1 and 2. The net force acting on the control volume during a steady flow is equal to the difference in the outgoing and the incoming momentum flux. It's almost a direct statement of Newton's second law. Questions? Okay. We'll start to see this in use in a few slides' time, and we'll go. Maybe some other questions will arise, some common issues. Something that we encountered when we looked at hydrostatic surfaces. How can we simplify situations where we have otherwise complex distribution of pressure? Here we have our control volume, and we're first saying that all the forces that are acting on this control volume can be split into 2 families, surface forces or body forces. As you would expect, surface forces act on the surface. Maybe less obviously, body forces act at every point inside the fluid domain. Surface forces include pressure and viscous force. which we introduced right at the beginning, pressure being the forces that act perpendicular to the surface, and viscous force is tangential. But most of the time in this course, we're neglecting the viscous forces. Viscous forces cause the flow to come to a stop near to a stationary wall. They're responsible for the no-slip condition. And in a lot of the analysis that we've done, we're neglecting the no-slip condition. We're saying it's inviscid. So, just looking at the pressure forces, what we can do, we can say, okay, there's a net change in the pressure around this control volume, which we can simplify by extracting the atmospheric pressure which completely surrounds it. And we can simplify this by just looking at the components of the pressure in the 1D direction of the flow. And this analysis is therefore still something we can do with our 1D equations. We've gone from something at the top right that looks quite complicated to something that we can then still use our 1D equations with. Always kind of look for the simplification that still means that you can get away with using the more simple equations. If you can solve a problem using a basic equation, then you should, absolutely. We're not in the game of overcomplicating things for the sake of it. But if there's a need, then we need to be aware of what the more complex alternatives are. So conversely, body forces act on every point in the fluid. So the obvious one is gravity. So we've talked about hydrostatic fluids, and every point in a fluid domain will be subject to a gravity force. So in a gravity, it's constant throughout the domain. A less obvious one is a rotational force, centrifugal or centripetal force. This one is a little bit more complicated because the magnitude of the force is proportional to the distance away from the axis of rotation. So we saw that a bit in the rigid body rotation problem. It's not going to be a constant body force. You need to know where you're rotating and how far you are at every point in the fluid from that. There's various other body forces like electric and magnetic fields that are beyond the scope of what we're going to be looking at, but worthwhile knowing that they are in that family. Okay. So while most of the analysis that you're going to be doing is 1D, there will be instances where you're presented with situations that require you to make simplifications in 2 dimensions. And the process for that, just like any other analysis, a free body diagram, which is essentially what this is to split it into the coordinate directions. Recognizing that the momentum equation is a vector equation. In the summary of the 2 equations that I gave you and repeated today, there was a comment at the bottom that the momentum equation actually represents 3 equations. And in the picture that we had of the full Navier-Stokes on Monday, that was clear as well. There's 1 equation for the conservation of mass and 3 equations for the conservation of momentum. And you can think of your resolution of your momentum equation here in the coordinate directions to be essentially the same thing. So you have a situation now where the forces and the velocities are not acting in the same direction. They can be in any arbitrary direction in the plane. You have to first split them into their component parts. Generally, bold font is used for a vector. It's not always consistent, so be wary of that. But when you're using a component, try to use a subscript of the coordinate direction, x or y. So here you've got the exact same equation, just in the x direction. So we've taken the component in the x direction and the y direction separately. And after that, it's essentially the exact same process. You do it 1 coordinate direction at a time. There's an example of that coming up. Okay, I think probably it's useful to go into some more practical examples. There's a bunch that we can do together now. So looking back at the jet impacting on a plate, you've got this nozzle propelling a velocity of water v1, hitting a plate and then being deflected by 90 degrees into the velocity v2. Even this can be, to some extent, could be considered as a 1D problem if you wanted. But for the purpose of the analysis, we're going to be looking at the the particular component of the force that's acting in the x direction. And in order to do that, we have to introduce the concept of Newton's third law, so the action-reaction. And this is where understanding what is included in the control volume and what isn't becomes really central. So if inside your control volume you have a physical object which is bringing the flow to a halt, then there's a force that is acting on the control volume. And that force F is something that will be balanced by the flow that's coming in and out of the control volume. All of the flow in this control volume is coming in the x direction, and it's exiting in the y direction. It doesn't matter that it's both vertically up and vertically down. In order to balance the horizontal force F, we only need to know information in the x direction. There's a reaction that's outside the control volume is felt in order to keep the structure stationary, and that is the force that's in the reverse arrangement, the water acting on the plate. Equal and opposite, unless you're told otherwise. The classic example, like I mentioned before, is propulsion. So whether it's a rocket or a jet engine in a test bed, the same thing applies. That the cut in the support is there to emphasize the cut that you make around the object that you're looking at. We said on Monday that the choice of the control volume is central to what you want to be able to answer in the question. And if you're looking to answer what is the force acting on the support, then you should cut it through the support, because the three-body diagram will leave you with a force there. In a jet engine, you have fluid propelled one direction, which imparts an equal and opposite reaction in the other direction, which is essentially the thrust. Right? Propellant ejected, you move in the other direction. In this case, the engine and the support is essentially the same thing. It can't move. So the force is transmitted through the support, and so the reaction is in the support going in the direction of the thrust. There's a question we'll look at about this as well later. Okay, so here's this one again. A water jet strikes a stationary plate with a mass flow rate 10 kilograms a second and a velocity 20. Find the force needed to prevent it moving. We make these assumptions. Velocity is acting, pressure can be neglected because it's open to the atmosphere. So then the only balance that we need to consider is in the x direction. The force is equal to the change in momentum flux coming in and coming out. Or the other way around, out minus in. It doesn't really matter as long as they're of opposite sign. And you will see in sometimes the questions, different coordinate systems are used. The essential is that you're looking at the difference between the momentum flux. X direction only. Mass flow rate is given in the question 10 kilograms per second. And you times this by the change in momentum flux, 0 minus 20. And so then the force required must be 200 newtons in the opposite direction. It's quite easy to get muddled between which force you're calculating if there's an equal and opposite reaction. So you have to read carefully the question. This is the question here is saying what force is needed to essentially to support the plate, to prevent it moving. And so therefore it must be going in the negative direction. If the question was what is the force from the fluid on the plate, then it would be positive. Got some time to discuss this a bit if anyone wants to. Yeah? What's your thinking? Yeah, absolutely. So, and then how do you go from an energy to the force? Huh? It would work. Yeah, my kind of follow-up question was how would you then, once you have the energy, that is you need to kind of absorb, how would you translate to a force? Don't worry if you don't know, just testing. So you're absolutely right. You can solve this question in many different ways, and you choose the approach based on the information you have. So energy is a force times a distance, so you need to. So the work done is essentially equal to the energy. The work done is equal to the force acting on it by the times the distance that it moves in. In this case, you would need to know. You would need to apply the Bernoulli equation. Is that still working? Yeah. Yeah. Okay. So, slightly more complicated question. What happens then if you double the velocity? Go on then.
You're probably going to end up with a double with a necessary global force being double. Because considering the x direction only, Fx is equal to mass flow rate times minus v1 x. You took v1 x and doubled it, so of course.
Okay, you're half right. The what do you? Any advances before I? Any further discussion? Any further points? And you explained it perfectly. So that you have the mass flow rate times by the velocity. But how do we calculate the mass flow rate?
We calculate the mass flow rate by multiplying the density, the volume, and the density, the velocity, and the area that
Yep. Yep, that's right. And so then you have velocity times velocity, so you have velocity squared. Exactly. Well done. So you have your mass flow rate, and you have the velocity that the fluid has to be reduced by, the change in velocity. Your mass flow rate is a velocity itself times by the density in the area, which results in a velocity squared. And so then the force is proportional to the velocity squared. And so if you double your velocity, you quadruple your force. Exactly. Which, as was pointed out before, quite correctly, it's like an energy, right? It's like a kinetic energy. So you have to completely negate the kinetic energy that the fluid has. Any other comments? Yeah? Excuse me? In this one? So what would solving for in the y direction give you? Is there a force acting in the y direction? No. So what you would have, it's a good question, it's a good comment. If you were to apply the momentum analysis in the y direction, you would have the same momentum going up as is going down. And they would cancel out and the net force would be 0. Let's say in a more complex situation, the jet isn't going in the x direction. It's slightly inclined. Then you're going to have maybe more mass going up than down, and there's going to be a net force in the y direction. In this diagram, there's no y force. There's a y direction, but we don't need it. Okay. Go on to this one. So, I think you're given up to here. You've got two scenarios. Flow is going in the vertical down direction, entering a tube, which is then curved. In the first case, the curve is a complete 180 degrees and ejects the fluid in the opposite direction. In the second case, the fluid only turns through 90 degrees and ejects in the horizontal direction. What is the reaction force in both cases, and which has the highest reaction force? Yeah? Yep, how come? Yeah, excellent. So the fundamental thing here is how much does the velocity change in the y direction? You can boil the whole problem down to that question. In the first one, well, let's start with the second one. In the second one, it has a vertical down direction, and then there's no y component after that. So it just goes down, and then it comes to 0. In the first one, it goes down, but it completely turns 180 degrees and goes out with the same magnitude. So it's changed twice as much. Yeah?
So for note's sake, you get a larger reaction force if you reverse the components than if you zero it.
Yeah, so think of it as the net change in the velocity. The net change. And this is where the coordinate systems are important. Because in order to fully understand the net change in the first case, you have to know that it's gone in one direction, and then it's changed and gone in the opposite direction. So the negative leads to a plus. So there's two kind of key points so far. Firstly, it's proportional to the velocity squared, and secondly, it's proportional to the net change in the velocity in the coordinate direction. Yeah? So we're just considering the y direction. So the question was, why is there no velocity here? Right? That was the question. Yeah. So we're looking at the y component, v out, comma y, and v in, comma y. I should have drawn a coordinate system, but y is vertical up. And so what you have is v in is going in the negative direction of y, but v out has no component in the y direction. So the total change in the y direction is simply v. Okay? Yeah?
Wait, so what happened to the x direction?
Good question. What do you think? In which case has a component of force in the x direction? The one on the right, yeah. Yeah. When there's a change in velocity in one direction, there must be a resultant force. So in case 2, there's a change in x velocity, because at the beginning it has no x velocity, in the end it has a positive x velocity. So there must be a force acting on the control system because of that. And it's very much like a propulsion force. There's going to be a reaction force needed in the opposite direction to keep that 90 degrees pipe stationary. Okay. I'm going to skip this one for now and just go to the next one because I think it's a more instructive one. If we have time, go back to it, or we will. I'll just upload the missing answer. So this is starting to get a bit more practical. We've got our jet engine. It's on a test stand, and we're given the thermodynamic properties of the air. We're told that the velocity is entering at v1 is equal to, 200 meters a second, and it's exiting at a much higher value of 1,000 meters a second. You're given the two cross-sectional areas, and you're told that in addition, fuel is added. So this starts to be a little bit more complicated. When we start thinking about cross-sectional areas and velocities and densities, we can immediately think of volume flow rates and mass flow rates. But when we have the addition of an additional source, we have to be careful. And this is starting to kind of go back to this idea that in our control volume, we have to account for sources and sinks, additional sources. Nevertheless, the first step is to find the density. And we use the ideal gas equation to do that. Something that you're given in your, if you were to do this in an exam, you're given the form of the equation and you're given the value of the gas constant, capital R. And so then you need to use pressure in its correct units and remember that the temperature that you need to use has to be in kelvins. So you should get then something that looks broadly right as a density, 1.18 kilograms per meter cubed, and then you can apply your control volume analysis. So we're here applying our green dashed box around the inlet and outlet, but also the inflow of the fuel. So our conservation of mass equation now looks like this. It has an extra term because there's a source term. Mass flow going in, mass flow going out, plus the source. It's still essentially a 1D problem. Okay, it doesn't really matter what is the direction of the mass flow coming in from the fuel line. Just treat it as a source. At this stage, we can still treat this as a 1D problem. So we have then our mass flow in. We're told that the fuel-air ratio is 1 to 40. So that means that we have to add 1/40th of fuel compared to the amount of air that we're putting through. Doesn't sound like much, it doesn't make a huge difference, but it's enough to mean that it should be accounted for. And in richer mixes where that number is larger, then it becomes increasingly significant, of course. So, if you know what the mass flow rate in is, you can work out what the combined mass flow rate out is by adding 1/40th to the inflowing mass flow. And then the last step is to apply the momentum equation. We're treating this like a 1D problem. We've not worried about the direction of the force, so we still treat it like a 1D problem. And we're looking at these forces F, which are either acting on the control volume or outside of the control volume. And we can put our numbers together and we can get this. So the mass flow rate out, 73.14, times the velocity out, 1,000, minus the mass flow rate in, 71, times 200, the velocity in is equal to this force. Note that we've had to calculate this additional mass flow from the fuel, and that's the key here. We've still treated it like a 1D equation, even though there's this additional term. And then there's a discussion about which is the reaction force and which direction is it going in. So F, the force needed to accelerate the fluid, so the force on the fluid it's the green one. That's the force that you need to add in order to reach the additional mass flow. And then the reaction force is the equal and opposite one, which is acting on the structure. Usually, if it's not tethered, then it would result in the acceleration in the other direction. But because it's attached to the stand, then it's the reaction force of the stand. Yeah. Mass flow of the force. This one. So here what we said was mass flow in plus mass flow of the fuel is equal to these two terms. So we're told that the fuel is 1/40th of the mass flow in. And then when we add that to the mass flow itself, it becomes 1 plus 1/40th times mass flow in. Yeah? Okay, so a nice question. Why didn't we account for the velocity of the fuel entering the fuel tank? the combustion chamber. Any ideas? Yeah? Yeah, I mean, this is where kind of a bit of engineering insight is needed. There's no one right answer, and actually, you could say it's an oversight. So it's a good comment. But what we could say as engineers is probably that velocity is low compared to the others. Maybe it's in the y direction, so it doesn't impact on the force in the x direction. Yeah. It's sufficiently small component in the x direction that we can ignore it, I think. Okay, so if there aren't any other questions, we'll stop there for today. And a reminder that next Monday we'll have this kind of a drop-in session, but no live lecture, no other lectures. Have a good weekend. I'll see you.